Okay, recording started. We're very excited to welcome Raf. Quick reminder to everybody to please mute their microphones. If you have a question, you can just use the raise hand feature and I will call on you to ask your question. So Raf, go ahead and take it away.
Thank you so much for having me today. I'll chat while I'm sharing the screen. Yeah, it's very exciting even to be virtually with you today. Yeah, thank you so much for inviting me. So today I'll try to share with you a little bit of an excitement that we had in the world of time domain astrophysics, I gave you the most generic title and abstract possible so that I could decide the day before what to emphasize. So I know that I will likely have a little time to touch upon what's going on with 17. So if you're interested in that, just ask me afterwards. There are some new observations that came in the X-rays that are really exciting right now. So I'll go very quickly here because a lot of you are experts in this field. So a slide to motivate why we should study transients, even if we don't care about stellar explosions. And here I put cosmology, I put chemical enrichment of the universe, galaxy feedback, and also production of these very, very extreme objects like black holes and neutron stars that are now detectable sources of gravitational waves. So the way I like to think about the problem is to spell out what are the big questions that are open questions in the field. So right now we are very, very skilled in observing a star when it explodes, but I think that there are a lot of ignorance on both ends, before and after that. So we do know, though, that a lot of massive stars, they do come in binaries, and sometimes they manage to stay together until the end, and they emerge on the Hubble time, producing these bursts of gravitational waves that we are all familiar with right now. So if I were to name the open questions that I'm trying to solve or elicit matter understanding into is, what are the progenitors of these stars? So what stars explode like what? What happens to these massive stars as they approach their depths? It's clear that what was sold to me as the theory when I was a grad student, that the stars will stay there quietly waiting for their death, is probably not an accurate view of what really happens. So what powers these explosions, what is the energy behind, and also what are the properties of these newly born black holes and neutron stars that are formed right after the explosion of stars. Last but not least, once we have these compact objects and they merge, how do they look like in the EM spectrum? So these are the big questions that motivate my investigation and investigation of my team every day. So there are big questions that have been there for a while. So I always try to ask myself why now is a good time from an observational perspective, especially to try to attack these questions. And I'm going to give you 2 points. The first is very much related to a technological revolution. So we are now in the era during which we can take pictures of the sky every night, multiple times during the night. So we can actually map the 4th dimension of the universe, which is time, in real time. And here I named some of the major facilities that are either operational right now, the young supernova experiment that I'm part of, and of course ZTF, and for the future, the LSST on the Rubin Observatory. This revolution is not only happening in the optical, but is also extending to other parts of the electromagnetic spectrum, and I very much hope that the high energy sky will also be able to follow with some more missions into UV and wide field X-rays too. Since I'm here, I also want to emphasize a new survey that is supposed to start pending all the COVID things in September 2022. You can think about the Las Chilias Mid-Southern Survey, LS4 in short, as half of a ZTF in the south. And the PI of the survey is Peter Nugent. You can see some brief specs of this survey. Is like a 20 square degree field of view. Probably we will use 2 filters, G and Z band. And the one thing that I care a lot personally is the fact that this survey will have more than 90% of the data public immediately. So all the products will be public immediately, which means that everybody, literally everybody, can use this data. This is supposed, the overarching goal is to complement LSST, and that's why we're using filters that are basically the same as the LSST one. So we will complement in cadence and in depth, in the sense when LSST saturates with LS4 observations. So stay tuned and finger crossed that things will really happen as we hope with COVID. And I always want to draw the attention to that little guy there in the picture. Always very amusing. All right, so what have we been doing with these new facilities? So of course, every time we put somewhere a new capability, we find new things, but we can also map better parts of the parameter space of things that we already know. And this is the case for supernovae that we were used to find around the peak, mostly because until 10 years ago, we were relying mostly on amateur astronomers. So we were missing out on this beautiful science that is related to what happens before the peak and even before the start of the main explosion. We do know by now, we do know very well observationally that stars are not quiet before exploding. And I find the study of the understanding of why the stars are not quiet one of the most exciting now in the world of massive stellar explosions. Of course, we were also able to find new types of transients. And here, the reason is because we basically went from type of monitoring that was not very dense in cadence to a much denser cadence monitoring, which allowed us to find very fast evolving transients, which is something I will talk about later in this talk too. And the other reason why we were able to find new types of transient is because we started looking somewhere else. So amateur astronomers tend to like beautiful galaxies. While the most interesting transient might not necessarily like those type of environments. And instead, looking in other types of galaxies like that sort of a smudge that they put there allowed us to find new types of supernovae, stellar explosions, including superluminous supernovae and F-bots, the fast evolving ones. So the other second half of the answer to this question of why now is a good time is instead related to the multi-wavelength approach that is very, very close to my heart. And I do see that as the first step towards what is now reality, which is multi-messenger astrophysics with neutrinos and gravitational waves. So point number one, in my mind, gives us discovery power. We can find new things in the sky. And by using all the wavelengths, all the photons produced, and also going beyond photons using neutrinos and GWs, we can actually achieve understanding. And this is a good way, discovery understanding, to actually make progress in a field. So let's go back to the whole world of questions that I'm trying to make progress in. And let me tell you how do we try to achieve this goal on a day-to-day life. So the motto here is no photon is left behind. So whenever there is something cool in the sky, and here I'm using the 18 cow transient, we repoint every single facility that we can put our fingers on. Those are the facilities that we triggered for the 18 cow event. And the attempt here is literally to put together a panchromatic view of the evolution of this transient and then put the physics on the different parts of the spectrum and try to constrain what is going on. As you might guess, it's not that these instruments are sitting there idle. So there is a sociological part of this game that I will be very, it's very happy to share about how to go along with try not to create too many enemies in your own field, stopping people while they're doing something else. All right, so we are now at the point in time where when we talk about discovery engines in time domain astronomy, they are no longer just made of a telescope. So once upon a time, a discovery engine would be a telescope, and that would be basically it. Right now, we do know for a fact that that is no longer enough. We always need to couple the telescope, so the data, with some software, some AI engine that is able to filter out let's call it the junk, anything that I'm not interested in too, and try to help humans understanding what is among the thousands of transients or things that are filtering the night, what is the anyhow one thing that I care about. So whenever the discovery engine, which is made of these two parts, finds something useful, that it gets sent to the follow-up team of students and postdocs that do the repointing of all of those facilities that you've seen in the previous slide. So going forward, so I'm going to start focusing with you on the first half of the question. So I'll start by trying to see where we are in this business of trying to understand what happens to stars that later explode. And here I'm talking about massive stars, so core collapses mostly. So we have basically three ways observationally to try and understand what happens before the main explosion. And the first is the simplest, the most direct you can think of, which is literally using the images that we collected of that part of the sky in the previous nights. And then we see if the star was detectable, if the star was doing something interesting. So this business was basically, it started off with 09 IP. So in my mind, Supernova 2009 IP, which was not a supernova in 2009, but most likely became a supernova in 2012, is the object that sort of woke up the community and told us that the stars that later explode are not quiet. And as you can see, the star experienced a number of outbursts that you can see in the years before the major explosion that is here at T = 0. So the important thing is that it was to realize that 09 IP was not alone, and other stars were doing something similar. The problem with 09 IP, though, we were lucky and unlucky at the same time, because 09 IP, just by chance, it did have HST pre-explosion imaging that was acquired in 1999. So what you're looking at there in this image is literally a picture of which star is creating all that mess 10 years afterwards. So by doing some modeling of the emission from this star, that is a progenitor of 09 IP, you would conclude that this star is extremely massive, so about 60 solar masses or so. And this was good and bad in the sense that it's great to have pre-explosion imaging. It allowed us to understand something about the star 10 years before. But at the same time, it sent a message to some part of the community that, you know, this sort of instabilities, this sort of outbursts, maybe they do not extend to the entire world of massive stars, but they just happen in the tail of this very, very massive stars. At the end of the day, they are less than 0.1% of the stars, so why should we care? So in the rest of this talk, I will try to show you how by now we do know that this type of eruptive behavior is actually shared by basically the entire spectrum of stars that explode as core collapses. And here I'm using, to emphasize this concept, I'm using Supernova 2020 TLF, a recent paper that came out just 1 week ago, led by my graduate student, Win Jacobson-Galan. So here you have an example of a supernova that is a common type 2P, type 2L, like supernova. So it's one of the most common ways that massive stars end their lives. And here in the inset, you can clearly see how at times of the order of 100 days before the explosion, which is at T = 0 in that plot that I don't think you can see my cursor, you can see that we were able to detect with pan-star emission coming from the star. So for 100 days, there is some detectable amount of emission coming from the star before it explodes. And this is the first time that we find this type of activity in a normal type 2L, type 2P supernova explosion. By modeling the spectra of the supernova, it seems to indicate that this progenitor belongs to a 10 to 12 solar mass star. So again, the message here is that, here I'm using the work by my grad student to emphasize this, but the message is that all stars seems to produce this outburst. Stars of all masses have been found to produce this type of outburst. So it's mandatory for the community to find a solution of why that is so. And I should emphasize that while this is the first case where we see directly this outburst with pre-imaging, pre-supernova photometry, there's been a lot of work done in the community, and a lot done by Tony actually, where the very bright UV emission from this supernova at early time was interpreted already as coming from the interaction of the shock with a lot of matter that was coming presumably from pre-supernova eruptions. So these observations are a nice confirmation of what theorists and modelers of supernovae already basically found from the modeling. So I want to bring home one message about 2020 TLF. If we put a 2020 TLF on a plot of a number of supernovae that experience this type of outbursts, it stands out because the level of activity before the supernova is at much lower luminosities, which fundamentally explains at least part of the why this activity was not detected in type 2L, type 2P explosions so far. Even if I have to say that it's clear that not all progenitors of the supernovae experience this activity at this luminosity. So the one thing that I want to emphasize is that if we place this supernova at 100 megaparsecs, so the supernova was instead at 38, 36, we can clearly see that the surveys that we have right now online, like ZTF or EASY, they're completely not able to find, they would not be able to find these eruptions that would fall way below the threshold. And here, the point that I want to make is that if there is a place in my mind, my personal opinion, there is a place where LSST can make a difference in the world of supernovae is in this world of pre-supernova eruptions. This is the place where LSST has a depth. The cadence doesn't really matter too much if these episodes are 100 days long. So LSST will be actually able to tell us a lot about this pre-supernova activity. Yeah, so this is what I just said. If I were to put places, discovery places in this diagram of luminosity versus timescales, I would definitely place the pre-supernova outbursts as one of the places where I do expect a lot of surprises in the next years, because of LSST and because of some other UV missions like ultrasat and hopefully some other UV mission approved by NASA. So the second way we do have to learn about the composition, in this case, of this material is through what is called in the field flash spectroscopy, where what it means is fundamentally getting spectra and very fast after the explosion. The idea is that we have a supernova, the shock breakout radiation, and the radiation from the interaction of the shock with matter can ionize material farther out. This material recombines, and by recombining, leaves some input as emission lines in our spectra. By monitoring the evolution of this emission, we can actually learn about the chemical composition of this material. There has been a lot of work done in the field, mostly led by the group of Avishai Gallian. And here I'm emphasizing again a paper by Wynne that is actually not in preparation, that is a mistake, it's now accepted, where you can clearly see that these spectra were taken very, very soon after the explosion, and you can appreciate how things change very rapidly. So from a technical perspective, this is very, very challenging, and this spectra happened thanks to the collaboration with Ryan Foley here. So you need to get on target. You need to realize that we have something cool in the sky, we point and get multiple spectra during the night. That's how the game is played. But the reward is really large because then we know the chemical composition effectively of the progenitor before explosion. And this same supernova 19 EHK was also, which is a calcium-rich transient. It was also the first calcium-rich transient for which we were able to detect X-rays with SWIFT, which leads me to the third point, which is shock interaction. So the concept again is very, very simple. We have a shock that is traveling through the medium. This process leads to particle acceleration. So we accelerate our electrons, we produce a lot of thermal and non-thermal radiation in the X-rays and radio. So the idea behind this whole game is that if our star was not well behaved before death, then the shock would see a disturbed medium in terms of density, and by monitoring the emission from this shock as it plows and sample this environment, we should be in the position to reconstruct the density profile of this environment. The beauty of this approach is that shocks from supernova explosions are very fast, much faster than the ejection velocity of material before explosion. That means that at any time t of my monitoring after explosion, I am sampling material that was ejected 100 times, 1,000 times t before the explosion. So if I do a good job and I monitor my supernova for 1 year, 1 year here on the ground, I am sampling the life of the progenitor in the previous 100 to 1,000 years, depending on the ratio between the shock and the ejection. So it does work, it does effectively work as a time machine. That's why I have a time machine symbol right there. So we have this incredible opportunity to learn about the pre-supernova life of these progenitors by using the shock as a probe of the environment. And here, and this is exactly what we do when we do X-ray and radio campaigns for diverse set of supernovae. And here is just a slide to show, if you're not a radio supernova person, how things look. You can see in the first diagram, is a spectrum, and it evolves from the gray lines to the light blue line with time, and it shifts. There's like a bell-shaped spectrum that shifts down in time, and by sampling the evolution of the spectrum, we understand shock velocity, and we can infer the density of the environment. So here, I go fast. I just want to emphasize how by doing this homogeneous as much as we can study of supernovae in the X-ray and radio, sometimes we come across surprises, and this was definitely the case with the supernova 2014C, that I can tell you that this was the first extragalactic supernova hydrogen stripped that was detected in the hard X-rays by NuSTAR. And after 2014, 2015 is the first time we got on target. After almost 7 years, it is still detectable by NuSTAR. So this supernova gave us the first X-ray, broadband X-ray view of a supernova evolution in 6 years after explosion. So we did, as usual, we tried to trigger everything we could. So we do know what the supernova was doing in the X-rays, in the radio, and the optical. And as you can see, the X-ray luminosity, which is the red stars, kept increasing, and it only now started to decrease. And the same did the radio. And instead, if we look at the optical, which is the lower panel, the DEF, what we witnessed was the emergence of H-alpha emission, which is extremely unusual in a nitrogen stripped supernova. So basically, we witnessed a complete metamorphosis from like a vanilla super normal hydrogen stripped core collapse supernova to a nitrogen rich supernova. So I know that by now you might already have in your mind the explanation for what was happening, and we were able to constrain that what was happening was that the shock of this supernova, which was hydrogen stripped at the time of explosion, crashed against this hydrogen-rich shell of material, which was sitting very close to the supernova, and contained, though, quite a lot of matter, let's say 1 solar mass or a fraction of it. So while we could describe very, very well the elements, ingredients in the environment that we needed to explain the phenomenology of the data that we had, we were left with one burning question, which was why? So why we have that material close to the star So we came up with two explanations, and one was that that material was left there because of the ejection of the envelope of the primary star because of some nuclear burning instabilities that are happening in the primary star. So in this case, it's a mechanism that knows that the end is coming. So the idea would be that if I were to do a careful job of follow-up of a number of supernovae, and this is the reason why this shell is sitting there, I should be finding these shells roughly around the same distance. The other option is that this has nothing to do with what is happening in the primary star, but we say, well, it's the fault is of my companion, and binary interaction is instead the reason that leads to the ejection of the envelope. And in this case, it is less clear if we were to expect, if you want coordination between the ejection of the envelope and the explosion of the primary star. So if in the case of binary interactions, we would expect less of a coupling between these two timescales. So based on n equal 1 event, as you might guess, there is no way you can distinguish between these two possibilities. And that's why we embarked since several years ago by now in this survey of trying to understand how many hydrogen-stripped supernovae do show evidence for interaction and when they do so. Here is a busy plot, but the shaded region is something that quantifies the ignorance about is the supernova interacting or not. So we don't have an answer for the sample of, in this case, 40 supernovae with VLA. So our goal in these years is to try to shrink these bars of ignorance and try to say, what is the fraction of hydrogen-stripped supernovae that at any time after the explosion are showing signatures of interaction or not? And I don't have an answer for you right now. So just to put together all the things about how we study these eruptions, we do have 3 different ways. We use flash spectroscopy, we use direct imaging, and then we use the shock as a probe. And the shock right now is the only way to get really far back in the life of a star, all the way to 1,000 years or so. So where are we trying to go from there? Well, we started doing something more systematic. And as you can see, there is clearly a line between when we do a good job in the monitoring and when we don't. And there is no science behind. The 1-year line is the cycle of VLA proposals or ATCA proposals. Well, the lifetime, not the cycle, the lifetime of those proposals. So we're trying to do something better and try to be better in convincing tax to give us time to continue monitoring our supernovae. But I want to share with you one recent finding that was completely by chance. So as part of our artificial intelligence effort to try to understand if something is interesting or not, at the time of explosion, we put together all the information that we can put our fingers on. So in this case, we were using the VLAS, the VLA Sky Survey, and trying to know if at that location in the sky, there is a known radio source or not. And by doing this exercise, we actually realized that there were a number of supernovae, old supernovae, like decades or more old supernovae that showed very luminous, very bright, but also very luminous radio emission. So we got intrigued and we started doing a study, and we found out that, yeah, there is quite a large number of supernovae that actually re-brighten at late times. And here's a plot from one of our proposals, just to give you a feeling. The paper is now out by Michael Stroh. So the blue points are, let's say, normal type 1 BCs, so hydrogen stripped. And you can see how the VLA supernovae that we found are those orange dots. They're really on the more luminous end. Is clearly a selection bias because of the threshold of VLAs. But it's kind of unusual to have so many supernovae sitting there if the behavior, the normal behavior, is that of the defining line that you can see that most of the normal supernovae follow. So we decided to enlarge our survey. Now we are doing a snapshot survey with VLA of more than 200 targets to try to complete our view of late time emission, radio emission from supernovae. So the reason why this is interesting is because between the supernova and supernova remnant world, there is a gap. And it's a gap that it's mostly a result of the lack of as many observations. But there are, in principle, a lot of beautiful things that can happen. And one would be that maybe we are seeing the evidence of a strong interaction with some very weird density profile in the environment. So that would mean that the evolutionary path of this supernova is really weird before explosion. Or maybe we are seeing finally some relativistic jet that was misaligned originally with respect to our line of sight. Maybe we're seeing that jet coming into our line of sight. Or as a third possibility, maybe we are seeing in the radio the emergence of a pulsar wind nebula emission, which would be really, really good and one of the first in the field. Question?
Yeah, so for these different hypotheses, so are these known supernovae that you're finding, they're brightening? So if they're known, you kind of know the distance and whether like the jet, interpretation or some of these interpretations are correct or not.
Yes, correct. And I was about to say, so most of those are most likely shock interaction with some unusually shaped environment. And we do have two candidates that might be consistent with a relativistic jet coming into our line of sight. And we do have one candidate for a pulsar wind nebula. And I would say for now, they're just candidates. So when most of these supernovae are, first of all, interestingly, most of these Vela supernovae are hydrogen fluid. And so most likely they are interacting with some overdensity in the environment much later in time.
And then just one more question. Do you have plans to follow up the sources that you do find, or do you just find them as part of the normal survey and you don't have to actually target them?
So the entire project started off with Velas. That was just by chance. Now we are taking images of all supernovae that happened, and our distance cut is 100 and something megaparsecs, and then we follow them up across the spectrum. All, yeah. The most exciting follow-up, in my personal opinion, is actually VLBI. For those that are bright enough and that we can potentially resolve, that is happening, and that can actually help understand what is the source.
Yeah, that'd be really cool. All right.
I might talk to you, Tony, about it.
Okay. Thank you.
Any other question? Okay. You are frozen on my end, so I hope the answer is no, and I go forward. Can you hear me?
Yeah, I think we can hear you. I think you're good.
Oh, awesome.
You're good to go.
Awesome. Okay, so I know I went because I'm about 10 minutes from the end of my time, so I'm gonna go a little bit quicker on the second half, and I just want to give you some highlights on another part of the parameter space that I think is really, really exciting, which is the world of very fast transients in the optical. So the reason why I find them particularly interesting is because I believe there might be windows into the life of black holes and neutron stars that are just formed. So I gave you the punchline. And the reason why I believe that is that while in the case of a normal stellar explosion, we do have this amount of ejecta around us that prevents us from seeing anything that is coming from deep down. For the case of the F dots, I do believe that we have much lower ejecta mass and potentially asymmetric, so that we have the possibility to see something that is happening deep down in the core at much earlier times. So back on this diagram, this is the other part of the parameter space that I think will be very, very interesting in the future. So just one slide about what these fast blue optical transients are, and then I'm gonna go and talk about, in my opinion, the most interesting finding. So as the name says, they are fast, so they go to peak much faster than the normal supernovae. They are the red stars right there. They are blue, so they tend to be hot. and they fade away. So if you compare to normal supernovae, that is where they land. And here our beautiful stripe of type 1As that allows us to do cosmology. Super luminous supernovae are up there, and then the normal core collapses are in gray. So F-bots are very fast. They cover a wide range of luminosities. And in my opinion, most likely that means that they're not a homogeneous, from a physics perspective, they might not be a class of homogeneous objects. So they might actually be heterogeneous in terms of their nature. So as any single time we have no clue what we're dealing with transients, we start studying environments. And all I can say is that until now, all the F-bots were in star-forming galaxies. So that means that we don't have to invoke, we don't need to invoke an old stellar population to explain them. So the very fast time scales of these transients and their very large luminosities, I'm very much interested in the most luminous part of this population, means that we can power them with the usual nickel 56. And the argument is a simple one. To power that luminosity, we will need so much mass of nickel that the diffusion time scale will be larger than the rise time. So that's why that can work. So we have two ways to solve the problem, which is adding an extra energy term in the equation. And then we can decide either to put that energy term deep down in the star or outside. And if we place it deep down in the star, this is a central energy or central engine. That's how it's named in the literature. Then the requirements on the surrounding mass is the same as for the nickel 56. So it's okay to put an extra energy term, but the mass around us needs to be small, or that energy will have no way to go through that mass on the relevant time scale. If we instead, we decide, okay, I don't care about the central engine, I put my energy source outside, maybe it can be a shock interaction with something, then we have a requirement that is about how fast my electromagnetic signal can vary with time, so a variability time scale. And for a long time, these views coexisted in the literature, and maybe they are not mutually exclusive. But the revolution in this field happened with the finding of this transient COW that soon became the cow for everybody. And this is the one for which we pointed everything. And I'm gonna go to the important thing, well, the part that I like the most about this transient, which is its X-ray counterpart. So here you have X-ray luminosity versus time. You can just focus on the black points. You can see a lot of variability with time that is very difficult to explain with a shock that is interacting with matter, unless we decide that the emitting regions is not the entire radius of the shock, but just some patches. And this is a very luminous transient in the world of the X-rays, and it does rival with the low luminosity gamma burst, for example. So the biggest surprise to me was what happened in the hard X-rays. And here I go back for just one slide on Compton-Hum spectra, that I'm sure for all of you that do AGNs of X-ray binaries are very used with, to deal with the spectra, but I was definitely not used to. So this type of sources, we do have reprocessing of the high energy source by material around it that creates that very, very typical Compton-Hum. So you have Comptonization of the highest energy photons, and then you have photoelectric absorption of the low energy photons. And then you also have this iron line. So now, if we take a spectrum of the cow, here is how it looks. And first of all, from a technical perspective, to put together this thing, we have to trigger 3 spacecraft and have them observing at the same time, which is an interesting challenge to start with. But you can see that we do have the normal power law of this spectrum, which is very typical. Everybody doing transients is very used to power laws. And then there is that hump. And contrary to what has been claimed in the literature, if you do model that data, so if you really try to put a model there, it's non-thermal. There is no way you can make it out with a thermal Bremsstrahlung spectrum there. And it also had a hump, sorry, not a hump, but a little excess of emission around 8 keV. So it does represent a ton, it does resemble a ton of those spectra of Compton-Hum sources. So our explanation is, in fact, something very similar. So our explanation is that this particular spectrum was the result of some high energy source of emission that was reprocessed by some medium around it. And in our case, though, the medium, the reprocessing layer, was the result of an explosion. So it was expanding on the relevant timescales of our monitoring. So at 7 days, when we looked at the spectrum and we got convinced that we had to deal with that hump, then the prediction was that if that layer was the result of the explosion, that layer should expand and lose with time capability to reprocess radiation. So in other words, the hump should have gone away. And if you see, that is exactly what happened. So the hump later disappeared. This is the first time that we see this hump in a transient, in an astronomical transient. So the interpretation is that we do need the source, deeply sitting source of X-rays sitting deep down. So very recently, there has been a claim of a QPO in a paper by DJ that was detected by NICER at very, very early times. And if this is really true, and if this will be confirmed, I believe that this is really, really evidence that this was the formation of some compact object, and we witnessed that in real time. And that's why I find this class of objects particularly interesting. If really this was a QPO from the formation of compact object, then we would know what that object was doing 7 days or 2 days after the formation, which is remarkable, I think. So just 1 minute, just to wrap up. This is definitely not the only object that belongs to the class of F-bots. There has been a lot of work, a lot of which done by Anna Ho here at Berkeley and before at Caltech. And the other interesting piece of information of this transient that we were able to find is the following, that these F-bots, if you put them in a plane where we are basically measuring the properties of their shock, of the shocks of explosions. So we have a plane of energy carried by these shocks and specific momentum. So these transients are able to power relativistic shocks. So for a transient named CSI 161010, at 100 days after the explosion, the shock velocity was 0.6 C. So this is very similar to shock velocities of gamma ray bursts. So the main message here that I would like you to bring home is that I didn't show you the spectra, but these transients do have hydrogen. So these transients are the same, for some perspective, they look like gamma ray bursts with hydrogen. So in other words, we have to deal with a new class of progenitors that have a hydrogen and are able to power relativistic shocks, and most likely maybe have jets. So I'm out of time, so I'm going to end here. If you're interested about the latest on Light 17, just ask me. I'll be happy to touch upon that too. And thank you so much for having me today.
All right, thanks a lot for the great talk. If people have questions, feel free to raise your hand, and we have plenty of time for questions.
For the NICER results, can you remind me what energy those are at?
So the QPO was 230, I think, 230 hertz.
No, what energy photons?
Oh, that would be soft X-rays, so it would be 0.3 to 10 keV.
Okay. So probably an inner accretion disk or a black hole, I guess, because a neutron star would be harder.
Yeah, I don't know.
I have a quick question for you. So for the F-bots, they're essentially all consistent with being in star forming regions. But can it be ruled out that some F-bots could be observed in old environments? Are there, okay.
So I think that what we know for sure is that all the F-bots that we detected were in star forming galaxies. And for the cow, which is the one at 60 megaparsecs, which is the closest one, we can rule out globular clusters at that location. however, I don't think we can say that every F-bot comes from a massive star at all.
What percentage of the F-bots have a host galaxy information? Is it a pretty small percentage?
It's pretty, yeah.
Can I ask a question on that more? So there's no globular cluster there? Is that from pre-explosion HST or post, after it's
Post. It's post-explosion HST, yeah.
So what's seen there after in post-explosion? Just nothing? Is this kind of disappeared?
Yeah, nothing. They put a limit. Yeah, it's in a star forming part of the galaxy, and they put a limit. I'm forgetting now what's the limit. I think the paper is by Lyman, with Joe Lyman, I think.
Okay, thank you.
Other questions?
You want to give us a quick update on 170817?
Yeah, I was going to ask the same thing.
Sure. Yeah. So very quickly here is it's a nightmare. So okay, we all know what 170817 is, neutron star merger. Now we all agree there was a jet. Great. And so we keep monitoring the source in the X-rays and in the radio. And to my surprise, I have to say, to my surprise, this source is still detectable in the X-rays. So first of all, that's a punchline. And the latest observations were from less than 1 month ago, and it's still detectable. I know it's completely unimpressive, but those few photons are really a very, very nice detection. And right now we collected 5 photons over 100 kiloseconds, and they're still detected. So now there has been a lot of discussion in the literature about is this consistent or not with the jet model. So here you have in blue the jet afterglow, but no matter what jet afterglow model you care about, you like at late times, it should all be a power law. What you can see is that the X-rays start to deviate. So here, the game is a game of very low number, a very low number of photons. So while I can say that the source is there, I can say what's the flux. So here, the game that we're playing is assuming that these photons are from that scenario of an afterglow. I can do a spectral calibration and I can give you a flux. So I'm giving the opportunity to the jet afterglow model to be right spectroscopically. And then I'm gonna look and see if I have deviation from a temporal perspective. And this deviation here is at the level of 3 to 4 Gaussian equivalent sigmas. The new, most recent observations from December 2021, they actually, because a source is there to start with, they do deviate by definition from the jet. But since the number of photons is 5 divided by square root of 5, you understand that it's not statistically significant on its own. But if you put all together the fact that we had 3 observations in a row that are all in access to the model is telling us that most likely something is there in the X-rays, and interestingly, is not there in the radio. So we found nothing in the radio, and we can't confirm right now a claimed radio source that appeared in the literature early last year. The good news is that we have 34 hours of relay time that we will all use to stare that part of the sky and see if anything is there. And later this year, Nora Trivia has a program in the X-rays with Chandra that she has a very large exposure, so she will be able to put the final word on it. So it might be a 3 to 4 sigma statistical fluctuation, which has a non-zero probability, or it might be something very, very, very interesting. And that would be my hope.
So what's the price per photon?
The price? A lot, yeah. But you also get money, right?
All right, great. So if there aren't any other questions, we can go ahead and thank Raffaella again for the great talk.
Thank you so much for having me, really. I hope to see you soon in person.
Yeah, that'd be great. So Raf, you have about 45 minutes and then your individual meetings start. So
Awesome. Thank you so much.
all right.
Bye.
Bye everybody.
Thank you.
Thank you very much.